Welcome to this explainer. Okay, so have you ever wondered why an AI can write this beautifully nuanced, brilliant essay 1 second, but then completely invent a fake historical event in the very next sentence? I mean, why do these highly advanced systems just suddenly lose their grip on reality? Well, today, we're unpacking some genuinely groundbreaking research by Jade Alglave and Patrick Kuzo. And I've got to tell you, this paper fundamentally changes how we view, how we build, and how we verify AI. They're introducing a semantic framework that literally forces us to rethink what an AI output actually is.
Right off the bat, let's tackle this massive question. We've all seen it happen. An AI gives you an incredibly convincing, perfectly formatted answer that is just absolutely entirely wrong. We casually call this an AI hallucination, but think about that word for a second. Hallucination implies, a psychological glitch, like a temporary lapse in a digital brain. Well, the researchers challenge this idea completely. As you can see by the broken connections we're highlighting here, when an AI confidently lies, it isn't hallucinating at all. It is actually experiencing a highly specific, verifiable engineering failure.
Okay, let's dive into this comparison because this is where it gets really interesting. The authors argue that right now, we talk about AI in two highly misleading ways. Over on the left, you see we often treat AI as magic or some kind of all-knowing oracle. We just assume that if the system generates a fluent, confident text response, well, that response must be an actual, undeniable fact, right? We completely conflate its ability to generate human-sounding language with its ability to state the truth. But on the right, this is the reality the authors present. AI is an engineered abstraction. It's a system built of distinct layers, and its behavior absolutely can and must be decomposed, interpreted, and rigorously checked.
To really make this mental shift click, the authors use a brilliant analogy. Think of René Magritte's famous painting of a pipe. Underneath it, he literally wrote, "This is not a pipe." Why? Because, well, you can't smoke it. It's just a representation of a pipe. The authors apply this exact same logic to AI, writing, an AI system's output is not the object it appears to describe, but rather a representation. So an AI generating a completed form isn't the actual truth. It's just a message that needs to be verified. It's a picture of a pipe.
So because AI outputs are just representations, the authors propose we start treating AI systems as semantic abstractions. What does that actually mean? Basically, it means using a really precise mathematical vocabulary to track exactly where the AI is getting its information from. This framework strictly separates three things. First, what is actually true out there in the real world. Second, what the official reference sources say. And third, and this is absolutely critical, what the AI system actually has access to in its current memory right now. This separation lets us track exactly what the AI is obligated to know before it takes any action.
Let's ground all this abstract theory in a real-world scenario. This is the exact example the authors use in their paper. Meet Oma. Oma needs to renew her passport, and she's using an AI agent to help her out. Now, this AI might need to look at her old passport, check the current government rules for photos, evaluate a new selfie she takes, and then fill out a form. But, life happens. What if the doorbell rings and Oma has to pause the application? What if she goes back and changes a form field later? The AI has to handle all of this chaos without making a single mistake that gets her passport rejected.
Now, what's really interesting here is how the researchers map out Oma's journey. Look at this timeline. They call this a trace of events. The AI doesn't just instantly jump to the end and submit the application. It has to record a progressive trace. It selects a route, observes the passport, checks the photo, does a readiness check, and then finally gets Oma's permission. Every single step along this path must leave a hard, verifiable record proving the AI actually had the authority to move forward to the next step.
So how does the AI actually process this trace? Let's build the architecture step by step. First up, the system pulls from knowledge bases. These are the official rules and guidelines. Next, an orchestrator takes over. Think of this as the manager controlling the flow of the application. Then it uses compute components, like a neural language model, to actually process the text and data. And finally, we have actuations. This is where the AI modifies the real world, like exporting Oma's final PDF. The big takeaway here: the AI isn't just a giant brain making guesses, it's a meticulously orchestrated assembly line.
To make this assembly line reliable, the researchers want us to think of the AI's inputs kind of like a funnel that filters down three distinct levels of knowledge. At the very top, the widest part is universal knowledge, the complete, ideal truth of the world. As we move down the funnel, we get source-derived knowledge, specific facts extracted from official references like a government passport website. And at the very bottom is effective knowledge. This part is crucial, so pay attention here. Effective knowledge is strictly what the AI actually has loaded in its narrow context window right at this exact moment.
Now, because the AI can only ever rely on that tiny bottom funnel of effective knowledge, its worldview is inherently lossy. It doesn't know everything. The researchers identify two specific mathematical limits that cause this. On the left, we have the ignorance abstraction, which is basically where the system simply drops facts that are outside its program scope. It just doesn't know them. On the right is the forgetfulness abstraction. This is where the AI literally loses the ability to distinguish between two concepts, perhaps blurring two similar passport rules together. This structural loss of information, this is exactly where mistakes are born.
And this brings us to a massive realization in the paper. Consider the moment the AI outputs a message that says check result message equals passed for OMA's passport. That event, that green checkmark on the screen, is not actually proof that the application is ready. That checkmark is just a message. It's Magritte's pipe all over again. Before the system can safely submit that passport, the underlying trace of evidence has to be checked to ensure the photo and the form were truly, factually validated against official sources.
And this brilliantly illustrates how the authors solve the whole hallucination problem. They take that vague, unhelpful buzzword and translate it into a precise taxonomy of verifiable engineering failures. So if the AI makes something up, it's not hallucinating. It is an information state mismatch. If it uses last year's photo rules, that's a stale source. If it says the form is ready but it never actually scanned OMA's passport, that is an unsupported assertion. We are moving away from mysterious AI magic and into clear, debuggable errors.
Let's look at how this actually plays out for OMA. In a traditional system, if OMA edits her form after the AI already did its check, the AI might just go ahead and submit it anyway. But under this new semantic framework, that error is caught immediately as a stale witness. The prior check is no longer valid. If the AI approves a selfie without checking the government database, caught as missing authority. And if the AI just hits submit while OMA is away answering that doorbell, that's flagged as a trace constraint violation because the system lacked her final confirmation event.
What's amazing is the authors didn't just write a bunch of math equations and call it a day. They built a working prototype app to prove this works as a real engineering discipline. In their system, a readiness check is not merely a green UI tick. It is a hard mathematical record of observations, witnesses, source support, and OMA's explicit confirmation. By enforcing this framework, they proved, without a doubt, that we can build AI agents that are accountable, verifiable, and just dramatically safer.
So the absolutely crucial points you should take away from this explainer are these. First, never treat AI outputs as facts. They are engineered representations. Second, if we want to build reliable AI, we have to mathematically separate universal truth, reference sources, and the AI's actual working memory. Third, we really need to stop saying hallucination and start diagnosing specific trace failures, like missing evidence or stale sources. And finally, if we want AI agents to take real actions in the real world, they must be grounded in step-by-step semantic justification.
Which leaves us with a critical, pretty provocative question to ponder as we move headfirst into the era of autonomous AI. If an AI's output, whether it's trading stocks, driving a car, or renewing OMA's passport, is just a representation of the world, what new trace safeguards are we absolutely going to need to mandate before we allow these agents to take world-changing actions on our behalf? This paper gives us the blueprint to start building those safeguards today. Thanks so much for joining me for this explainer, and keep learning.